In this video, we are going to study the parametrized post-Newtonian formalism. This formalism arises as a generalization of the post-Newtonian approximation to general relativity that we have reviewed in the previous video. The idea of this parametrized post-Newtonian formalism is that you will have many theories, which are metric theories of gravity. All of them must admit some post-Newtonian approximation, because otherwise you will never recover Newtonian gravity, which we know works so well. So, if you have many of these theories, maybe their post-Newtonian approximations can be related, okay, and they can be parametrized. So you have a number of gravitational potentials, and the metric depends on those gravitational potentials in a way that is controlled by those parameters that, to which the name parameterized refers to. Okay. Maybe if I write the metric in terms of those potentials and those parameters, you will understand probably better what I am saying. Okay, so the parameters that are introduced in this formalism, I have to say that first that the original idea of this formalism was by Eddington, and then Northvet, the one of the Northvet effect, made a more sophisticated approach to this formalism, and finally this final form is due to Clifford-Will, essentially. Okay, the parameters that enter in this approximation are gamma, beta, psi. There is alpha 1, alpha 2, alpha 3, and there are Z1 to Z4. You see that there is no alpha parameter, okay? In the original formulation by Eddington, alpha was there, but I will tell you where and why it doesn't make much sense to introduce this alpha. This is almost a definition, okay? In this formalism, G00 is assumed to be of this form, okay? So you have this potential that we know is the Newtonian potential. Then there is a term over 1 over C4 of this form, psi minus beta u squared. Then there is another term, okay, and to the same order that we have studied in the general relativity case. Okay, apart from the fact that this is slightly different, you see that there is one more gravitational potential here. There is, I have written here PF, because these potentials arise in theories in which there is a preferred frame. Okay, this is not the case of general relativity, so this is why you don't see this any potential like this at this order. And there are more of this kind. So certain theories are not completely covariant in the sense that there is a preferred frame for them, and then effectively this introduces another gravitational potential in the metric. G0I is given by 1 over C cubed. The orders are the same because the arguments that led us to expand the metric in the way we did it for GR are exactly the same. But of course, this dependence is different. So this is 2 times 1 plus gamma plus a half of alpha 1 and multiplied by the potentials ui plus 1 over 2 C cubed, and then a bunch of terms. Okay, 1 plus alpha 2 minus Z1 plus 2 psi, and then partial t partial I of x. Okay, that I will, whose expression I will give you later, but this is basically the f that we, or related to the f that we introduced in in general relativity, minus 1 over C cubed psi I, and this is a collection of potentials that are also arise in theories in which there is a preferred frame, and again to the order 1 over C5. Okay, finally, the expansion for Gij is minus 1 plus 2 over C squared gamma U delta Ij plus terms of order 1 over C4. Okay, this is a definition of the potentials, and if you want, it will be our ansatz for the metric. In the original formulation by Eddington, alpha, the parameter alpha, was here. Okay, and you see that we know that this is the Newtonian potential. Okay, and if this parameter doesn't have the right value, you don't recover the Newtonian limit. So theories which have alpha different from the value that gives you exactly this are just not good theories. They cannot be accepted. And in this sense, you don't need to consider theories with values of alpha different from the right one. So, well, it doesn't make sense to introduce this parameter alpha, and it has been eliminated from this formalism. Okay, although, well, the name has not been used for anything else. Alpha 1, alpha 2, and alpha 3 are something different from alpha. Okay, this psi that is used here is slightly different from the psi that we used in the previous case. So this psi is given by a horrendous combination of parameters. Of course, you don't need to memorize anything like this. The idea of these sections of the program is that you learn, okay, how to use this formalism and the meaning of all these things, and not that you memorize all these complicated expressions. This is phi 2 1 plus Z3 phi 3 plus 3 times gamma plus 3 times 4 minus 2 psi, sorry, this is a 3 phi 4 minus half phi 6 minus psi phi w. Okay, this is essentially the definition of psi. You see that the fundamental gravitational potentials are this, okay, and phi w. Then, okay, the formalism is completed by giving you the expressions of these potentials in terms of the variables that appear in the energy momentum tensor at in the Newtonian approximation. These kind of expressions are, well, remember that U is given by G times this integral, so the solution of the Poisson equation. Okay, this is U of t and x. And I will give you the rest of the expression of the rest of the terms in this expansion. But just observe that, of course, this has to be exactly the same. Otherwise, there is no correct Newtonian limit. The Newtonian potential has to be given by this solution to the Poisson equation. Okay. So for the rest, I will just copy the result from the lecture notes where you can find all this. And by the way, this has been taken from Poisson and you will do well to check it and study that book. Okay. Well, here it is, and you see that indeed x is what we called f in the general relativity case. We had essentially in that case this u, this ui with exactly the same expression, And yeah, all these 5, 3, and other of these potentials, like this one, they also appear in this separated, okay, or combined rather, in the solution to the small psi equation in the general relativity case. Now, this combination, of course, can be different for different theories of gravity, and this is why you have separated this solution to a single gravitational potential into the solution of several different gravitational potentials, phi 1, phi 3, and so on. And there is a particular combination of these potentials that gives you what appears in general relativity, and well, other combinations correspond to other theories, or the other metric theories of gravity, and well, always in the post-Newtonian approximation. With respect to these preferred frame potentials, this is the velocity, this is omega I, that appears here is the velocity of the frame in which you perform this post-Newtonian approximation with respect to this preferred frame. Okay, sometimes you can set it equal to 0 if you decide to work on the preferred frame, but in those theories that admit a preferred frame, it is not clear that you are going to perform your experiments in that preferred frame. So you need to introduce these potentials have a non-trivial value. Okay, do these parameters have any particular physical meaning? Okay, so let me just copy what appears in Poisson and Will's book about these parameters, and also what are the values that they take for general relativity, because general relativity is just a particular case of this family of theories described by the formalism. Well, in this table you can see the parameters, the value they take in general relativity. So the convention for the first parameters, alpha, which is not now is not used, beta and gamma, is that they take the value 1 in general relativity. Okay, here you see it. Then, well, for other theories, they take different values. There is a whole class of theories which are called semi-conservative, and they take different, for them, gamma takes different values. The same happens with beta. This parameter psi, which measures in general preferred location effects. So there are two different things, preferred location and preferred frame. Okay, for preferred frame, this is controlled by the parameters alpha 1, alpha 2, and alpha 3. In general relativity, because of it satisfies the principle of the Einsteinian principle of equivalence, there are no preferred location effects. It doesn't matter where you perform experiments. Okay, and here the conventional value is 0, and there is no preferred frame either. There are no preferred directions in space-time, there are no preferred velocities, anything like that. So all these parameters that control this give you take the value 0. Okay, and in other theories you have other possibilities. Is total momentum conserved? Well, yes, in general relativity this is controlled by all these parameters in general. So really this formalism encompasses very general classes of theories, some of which you could say, okay, I don't like theories in which momentum is not conserved, but okay, there is a challenge to exclude them experimentally. And then you have to perform, ideally you should perform experiments in which you measure the values of these parameters, or unless you constrain their values. Concerning the physical meaning of these parameters, well, gamma, okay, has this meaning of how much spatial curvature produced by the unit rest mass. We are going to see that in a minute in one example, but okay, spatial curvature is probably related to the spatial components of the metric, so gamma appears here. If gamma was 0, there would be no curvature or spatial curvature. because this would be the Minkowskian value. Okay, and general relativity gamma is 1, and if you remember what was the value of this factor in the general relativity case. Beta gives you an idea of how much nonlinearity there is in the superposition of gravity. This is about the self-coupling, the coupling from gravity to gravity. This is a more sophisticated thing, but okay, let's look at the place where it appears. It appears here, multiplying u squared. Okay, there's not much to read from there, but apart from the fact that, of course, here you have well, gravity coupled to gravity, if you want. There is the Newtonian potential squared. Okay, so now probably you want to consider different kinds of matter, solve for these potentials, and then what would be the next step? Well, the next step, if you have found the potentials, you have determined the metric in terms of these parameters, the general PPN metric to first order. Well, you can now compute, find the geodesics and study things like the shift of the perihelion of Mercury or other objects in the sky, or the deflection of light, but always depending on these parameters. And okay, if you devise experiments in which you can determine the values of those parameters, you can check if general relativity is right, or you can exclude theories that predict values which are outside of the rank allowed by the experiment. So that's the idea. And the simplest kind of matter that you could consider is a point particle at rest at the origin in our reference frame. So this is something described by a rest mass density, which is given by this rest mass times the Dirac delta at the origin, and all the rest of the variables that appear in the energy momentum tensor vanish. The velocity vanishes, the internal energy vanishes, and the pressure vanishes. And okay, for simplicity, we are going to consider that there are no preferred reference frames or anything, and in any case we would set this omega is equal to 0. This is just for simplicity because we don't want to consider the more general case, which could probably be too complicated. Now we just follow the program. You have the variables that determine the matter, that describe the matter that you have, and you just plug those variables into these equations and compute the gravitational potentials. Okay, as simple as that. So now you get that u was g and the integral over y of rho star t y divided by y minus x, and because this is just m and a delta, you just get this evaluated at y equals 0, and this is just g times m, and this evaluated at y equals 0, which is x. This is what we call minus 5. Okay, very easy. Really, x is g, the integral, and now you have rho star t y, and it's multiplied by this expression, and so you get gm, and this delta gives you x multiplying. And the only other non-vanishing potential that you get is phi 2. Okay, in some cases you just see it because v is different, the velocities are 0, so automatically some of them are 0. Only phi 2 can be different from 0, and I don't do the calculation because it is really simple. Now you have to plug u and rho star, and what you get is g squared m squared divided by x squared. Phi w is a complicated combination of x, u, phi 2, and so on, but you can check that this identically 0. And then psi is minus 2 beta minus 1 z2 minus psi times phi 2. Okay, so these are the 4 potentials which are different from 0, and you just have to plug this into the general form of the metric to find a metric that depends on all those parameters. It doesn't depend on all of them because some of these potentials vanish. Okay, this for instance vanishes, so well, I don't remember if alpha 1 appears in more places, but certainly if it only appears here, you will not see alpha 1 anymore. Okay, so this metric, it does not contain all the parameters, which means that you cannot prove their value by just experimenting with this gravitational field. You need more complicated fields, probably with rotations, velocities, and so on. Okay, so if I plug all these, as I said, in the metric, what I get is that g0 of 0 is 1 minus 2u divided by c squared minus 2 divided by c4 and 1 minus 3 beta plus z2 plus psi u squared plus terms of higher ordering 1 over c6. G0i is 0 to this order, so it's 0 plus terms of order 1 over c5, and Gij is minus 1 plus 2 gamma divided by c squared u delta ij plus terms of order 1 over c4. And now by inspection of the metric, since this combination only appears here and always in this form, we're going to redefine this as minus beta, which would be the traditional value of this. Plus, remember, and this is something that I noticed, that in this case, psi h2 beta u squared is what corresponds to capital psi in the general relativity case. So now this metric only depends on beta and gamma, and in terms of functions it only depends on u, which we just saw that it is gm over r, if you want. Okay, so all these theories give these metrics corresponding to the gravitational field of a massive particle at rest at the origin. And let me remind you that this is just an approximation to the gravitational field of a spherically symmetric object when you are far away from it, so you can ignore the size in particular of this object. And this is which is a quite good approximation, as we know. And we will we could also incorporate other effects like obludness and so on by using the appropriate modified rho star. Okay, but in this course we are going to consider only this spherically symmetric field. If I write this in the standard way, as this takes this form. So this is plus 2 divided by c4 u squared dt squared minus 1 plus 2 gamma u divided by c squared dx squared. Okay, this would be the line element that we are considering. So, well, if I told you that the values of beta and gamma are 1 in general relativity, this is something that we saw, but you can also recover it by studying the Schwarzschild metric. The Schwarzschild metric should admit a post-Newtonian expansion of this form, and with sorry, something happened to beta. And from it you could read the values of beta and gamma. But you see that in order to compare the Schwarzschild metric with this metric, you have to rewrite the Schwarzschild metric in this kind of coordinates. We gave the Schwarzschild metric in this form, okay, minus the r squared divided by lambda minus r squared the omega squared, where lambda is just 1 minus 2gm over r. And the main characteristic of this metric is that there is a common factor multiplying the x squared. The x squared, which in spherical coordinates would be the r squared plus r squared the omega squared. So there is a factor multiplying everything. This is what we called isotropic coordinates, because there is a common factor multiplying something which is the same in every direction. Okay, so how do we go from these coordinates to these coordinates? Well, these clearly you have to change, you are not going to modify the angular coordinates because this you want it to be just the same. So you have to redefine the radial coordinate. You are not going to touch the time coordinate either. And okay, suppose that you introduce coordinate rho. Okay, so now r will be a function of this new coordinate rho. We call it rho for the moment, and at the end we will call it r again. So if you change from r to rho, lambda will be now lambda of rho after you change this, but there is nothing else to take into account here. Okay, here I should write probably a c squared if I want to keep all the factors of c. And okay, you have 1 over lambda dr the rho squared the rho squared minus, now this is r of rho squared. This could be a function of rho. So I divide by rho because I want to make rho, okay, explicit here. So under which conditions I can take a common factor of d rho squared plus rho squared d omega squared? Well, if this is equal to this, okay, these two things are equal, and well, sorry, not this one. These two things are equal. You don't. This will be here. Okay. So this is the common factor, and now you can write this as a differential equation. This is 1 over lambda dr the rho squared has to be equal to r squared divided by rho squared. Well, you bring all the r's to the left hand side, you take the square root. So this would be 1 over lambda 1/2 dr divided by r equal to d rho divided by rho, and you integrate and you choose the integration constant such that, this is probably something that you also want, such that when r goes to infinity, rho also goes to infinity. Okay, if you do this, well, you find that the relation between r and rho, this calculation is done in the lecture notes and it's trivial. You just have to do this integral. Gives you this relation between r and rho, this square divided by rho. when I wrote lambda before, I missed the factor of c squared. So lambda is 1 minus 2 gm divided by c squared divided by r. Now you perform this change of coordinates. Now you have to start all over again. You differentiate here, so you take now the derivative of all this with respect to rho, operate and so on, and what you get is a metric that you can write in this form: ds squared is 1 minus rs divided by 4, 1 plus rs divided by 4, here rs, okay, and divided by r. So I call rho r again, just because it is customary. So c squared dt squared, rs is the Schwarzschild radius, so it is this constant, 2gm over c squared, plus 1 plus rs divided by 4 and divided by r squared, okay, and with a minus in my conventions, of course, and the x squared. Okay, so let's you just have to perform the weak field expansion and everything, and it is not so difficult to do. Okay, you just consider small values of rs with respect to r, and the expansion is 1 minus rs divided by r, which is good because, well, we will see now that you recover. Then this is the Newtonian limit. Rs divided by 2 squared divided by r squared, and this multiplied by c squared dt squared minus 1 plus rs divided by r dx squared. Okay, if I restore these values to gm divided by c squared and so on, okay, I find that this is gm, so this is gm squared divided by c fourth r squared, and then I compare with this value here. Okay, remember that u is just gm over r. Okay, and well, what I get here is that I get the right value, and here I get that beta is equal to 1, and here that gamma is equal to 1. Okay. So the next thing that one has to do in order to find predictions of this family of theories is to, if you want to study this, if the predictions are based on the motion of particles or the propagation of light, you have to compute the Christoffel symbols to study the geodesics. This is a straightforward calculation, so I will just quote the result that is given in the lecture notes, and this is the result for the non-vanishing components. As you see, gamma 0, 0, 0, and gammas with 2 spatial components and 1 time component are vanished, at least to the order that we are considering in 1 over c. Okay, this simplifies somewhat all the calculations. Now you can plug this into the equation that we derived for the acceleration, for the Newtonian acceleration. Okay, this was an expansion that depended on gammas and velocities, and the result is that in the end, okay, x double dot I is minus, well, the Newtonian term plus 1 over c squared, this correction, as we exactly what we wrote in the general relativity case, but now eta I, okay, contains these terms. Remember that eta I contained a lot of terms in the general relativity case, but that was because it was the general relativity case with non-vanishing velocities, non-vanishing internal energy, and so on. And here this is eta I just for a particle at rest at the origin. Okay, so this phi is already determined. Okay, phi is minus gm divided by r. Okay, and this is the formula that determines the motion of particles in this approximation. As I said, this formalism allows you to compute more corrections. Okay, we are dealing with the simplest case. I think that if you study Weinberg's book, you will find corrections to the standard Newtonian orbits that depend on the oblateness of the sun and so on. And those are some of them are Newtonian corrections, because what you would find could be just different forms of phi. Okay, so they are corrections with respect to this simple potential. So in this sense, they are not post-Newtonian corrections, but you can incorporate a lot of effects. In the next videos, we are going to apply all these results to the study of the deflection of light in a gravitational field. So when the light passes close to the sun or another star, also the radar echo delay or the Shapiro delay, and again the shift of the perihelia of astronomical objects. So they will be called peri-astron or pericenters, but using this metric in this approximation. And then we will recover the predictions of general relativity when we set beta and gamma equal to 1. This is why we have not done these calculations in section 6.2.